Hello and welcome to Calculus Lesson 7.2, Dot Product. All right, so let's just revisit what a vector is. A vector has both magnitude, so that would be its size or its length. Okay, so this is how long it is. And it has direction. Okay, so let's look at two vectors. So let's say I've got vector A and I've got vector B. B has a larger magnitude than A and it's going in a different direction than A. Their angles are slightly different. Now, how can I relate vectors A and B together? Well, one way to relate the two vectors is by taking something called the dot product. So the two vectors can be multiplied, and I'm, of course, being careful with that word multiplied. It's not direct multiplication, but it is multiplication. You can multiply them using the dot product. So essentially what the dot product is an operation that you can apply onto two vectors at a time that allows you to see how similar they are relative to one another. So A dot B is equal to the magnitude of A times the magnitude of B times cosine of the angle between A and B. So that is the formula for dot product. Something important to understand is that when you take the dot product of something, and you can see this from the formula as well, even though you're dotting two vectors, the result is the magnitude of one vector, that's a scalar, times another scalar, and cosine of theta is another scalar. If you multiply three scalars or three numbers together, you get a scalar. So the result is a scalar, not a vector. Okay, so you should just get a number as your answer. Okay, so what that means is if I have vector A and I have vector B, so let's actually place them tail to tail. So here's A, here's B. Theta is the angle between the vectors when they are placed tail to tail. Okay, and that's always the case. Okay, so then the magnitude of A is the length of that vector A. So this is the magnitude of A. And this here is the magnitude of B. And of course, there could be various ways in which we figure out what the magnitudes are. Okay, so let's just state that here just to make it formal. So absolute value of vector A is the magnitude, also known as the length of vector A. Absolute value of B is the magnitude / length of vector B. And theta is the angle between vectors A and B when placed tail to tail. That's very important. Okay, so the vectors will always be given tail to tail, so you'll have to figure out a configuration that allows you to determine the angle. Okay. So again, this is one way to figure out the dot product. If you know the magnitude, if you know the angle between the vectors, done. You can plug in those values and multiply the three numbers and you have your final answer, some number, which is the dot product. Okay, so this is one way to do it. Or you can take the dot product of Cartesian vectors. So this entire chapter is on Cartesian vectors. So we saw in the last video that a Cartesian vector is essentially a vector that you represent with an x component and a y component in a series of brackets. So something like this. So A comma B. All right. So in this case, there are two vectors. We have A and B. So let me just sketch those again. So we've got A, we've got B, and here I've drawn them tail to tail. So B is up here, A is here. I'm writing the letters in a different spot because I'm going to show you how to figure out what the x and y components of each are. So if I break these up into their components, so assuming x is horizontal and y is vertical, I can break A up into vertical and horizontal components. So it would look like this. So the y component would be going up. Oh, sorry guys. The y component would be going up and the x component would be going right. So I have here ax and ay. Now, those are the vectors, and if you want to know the length of each of those sides, that would be the magnitude of ax and the magnitude of ay. So similarly, bx is the vector going to the right, and by is the vector going up. And of course, those are 90 degrees. Okay, so what that tells us is that vector A we can represent as ax, comma, ay, and the vector B we can represent as being bx, comma, by. Now, this was one formula for dot product. If you have their side lengths, you have the angle between them, go ahead and use this. If you just have the vector components, a much faster way to figure out the dot product is like this. A dot B is equal to the product of the x components plus the product of the y components. So this is the other way to do it. Otherwise, figuring out the magnitude of this and then the magnitude of this and then determining the angle between them, well, it's going to be quite long. So there you go. Okay, so now that we have that, let's try an actual problem. All right. So example 1. Okay, so dot product is used in physics quite a bit. So assume you have some kind of a ramp, okay? And you've got a box on that ramp. So those of you in physics, this scenario is going to seem extremely familiar. So there's a box on a ramp, and so let me just indicate that here. And a force is applied onto the box. Perhaps there is a rope attached to it, okay? And there's a force of tension of 120 newtons being applied in that direction. Now that direction is 20 degrees above the plane, which is parallel to the ramp itself. So the ramp is that piece up there. Now, with this force exerted at that angle, the box undergoes a displacement of 100 meters. And the question then becomes, how much work is done on the sled? So those of you that are not in physics, you're probably sitting there scratching your heads wondering, what is work? Okay, so in physics, work is defined as the product of force with displacement with cosine of the angle theta between the force and the displacement. Okay, so we can call that delta D. Now, what we see is that, well, if you look at the magnitude of force and you take the magnitude of the displacement and you multiply that by the cosine of the angle between the two vectors f and delta D when placed tail to tail, that's the same thing as saying work is equal to the dot product of force and displacement. Okay, so we're going to go ahead and use this interpretation. So those of you, again, not in physics, since you've never seen this formula, anytime you're asked to calculate work, that means you're taking the dot product of force and displacement. So let me just take and put these vector symbols on top. Okay. All right. Now, if I just do a quick sketch of this scenario, I've got my force. Okay, I know that's 120 newtons. Now, this thing is getting displaced up the ramp in this direction. Okay, so if that's the direction of delta D, well, that's at 20 degrees to the force when they're placed tail to tail. So force is like this, displacement is like this. The angle between them when placed tail to tail is 20 degrees, so that's the angle I get to plug in my formula. So force magnitude is 120 newtons. The displacement is 100 meters times cosine of 20 degrees. Make sure your calculator is in degrees. Okay, so here we go. 120 times 100 times cosine of 20 degrees. Okay, so we get approximately 11,276. And the unit for work is joules. I'm sure you've seen that unit before if you've taken other science courses, but there you go. And what we see is that this is, in fact, a scalar quantity, as we would expect. The units that come out depend on the application. This is one important application of dot product, work. So you got to remember this formula. and you got to remember the units. Okay, so the units are J, and J stands for joules. Of course, you would have seen that in grade 9 science. All right, so let's keep going. Example 2. So in example 2, we're going to determine the dot product. All right, so we're going to have 3 scenarios here, A, B, and C. So in scenario A, we've got one vector here. We know its magnitude is 20, and I've got another vector like so, and its magnitude is 15, and the angle between them is 30 degrees. Okay, in the second case, I've got one vector going to the right, so the magnitude of that vector, which we'll call D, is 13. I've got another vector going to the left, just slightly shorter than that one. The magnitude of C is 10, and the angle between them is 180 degrees. And in the last case, I've got vector E, whose magnitude is 5, and vector F, whose magnitude is 3, and they are at 90 degrees to each other. Okay, so let's start off here. So dot product, so that means here I'm looking at the dot product between vectors A and B. Now, because I'm given the magnitudes, that just goes to show that this is here vector A, and this here is vector B. So I'm looking for the dot product between A and B. So A dot B is equal to magnitude of A, magnitude of B, times cosine of theta. Okay, and theta, again, it has to be when they're placed tail to tail. And sure enough, in the picture they are. So magnitude of A is 15, magnitude of B is 20, times cosine of 30 degrees. So this is just a matter of punching in our values. 15 times 20 times cosine of 30. So about 259.8 or 260 if you want to call it that. So about 260. No units here. Okay, just the final number answer. Okay, next we have same thing. We have 2 vectors. We have vector C and we have vector D. So we are taking the dot product of C and D. So that's equal to magnitude of C, magnitude of D, times cosine of the angle between the two. All right. So magnitude of C is 10, magnitude of D is 13. And this time we multiply by cosine of 180 degrees. Well, cosine of 180 degrees is minus 1. Okay, so that means we have minus 130. Now, if you're wondering at this point, well, what does it mean if a dot product is positive or negative? Well, that, excuse me, it really depends on the application. So for example, in the previous application, we saw that work is an example of dot product. It's force dotted with the displacement. So if that dot product turns out to be negative, it actually ends up at a very interesting conclusion. And that conclusion is that an object ends up losing speed. It loses kinetic energy. Not something that you need to worry about, but for those of you in physics, this is just a further reinforcement of what we've already seen. Okay, part C, E and F. So I've got vector E here, and I've got vector F down here. So E dot F is equal to magnitude of E, magnitude of F, times cosine of theta. So 5 times 3 times cosine of, and sure enough, that angle there is 90 degrees. Now, cosine of 90 degrees, that's 0. Okay, so it doesn't matter what these first two numbers are. If they are at 90 degrees to each other, the dot product is 0. And so what we start to notice is that there's this huge reliance on the cosine of the angle. Sure, you get the product of C and D, but it looks like the dot product varies. It can be at most AB times the maximum value of cos theta, which is 1. Right? So at max, it can be A times B. At its lowest or most negative value, okay, let's say most negative value, it's going to be a times b times -1, right? So because -1 is 180 degrees. And at its, well, smallest absolute value, if the two vectors are 90 degrees to each other, if they're perpendicular, we see that the dot product is 0. And again, these applications only make sense when you actually apply them to real-world scenarios, like in physics. Okay, so what I want to do now is look at a graph of cosine of theta. Just quickly. So hopefully you remember what cosine of theta looks like. So we've got cosine of theta. Let's produce our horizontal axis here. So that's theta. So let's go up to 360 degrees. Okay, so half of that is 180, and half of that is 90, and then the 3/4 point is 270 degrees. Now I know that cosine of theta ranges between 1 and -1. So my graph looks something like this. It's concave down between 0 and 90 degrees. It's concave up between 90 and 180. Between 180 and 270, it's concave up. And between 270 and 360, it's concave down. And oscillating between 1 and -1. So what I notice is that in these intervals, so when theta is between 0 and 90 degrees, so there's 0, and when theta is between 270 and 360, the value of cosine of theta is positive, right? So it's positive here and it's positive here. When theta is between 90 and 270, it's negative, right? Cosine of theta is negative. And at these two particular points, at 90 and 270 degrees, the cosine of the angle becomes 0. Okay, so based on this, well, I can come to, well, an interesting conclusion. Aside from what we already discovered here, we can come to the conclusion of one of the significant properties of the dot product. Okay, so here are some properties. And the first significant property comes from the fact that if your two vectors are perpendicular, so if they're at 90 or 270 degrees to one another, well, your dot product is 0 because cosine of the angle will just be 0. So if you have vector u and you have vector v, right, and they're 90 degrees to each other, so that angle there is 90 degrees, or so that's 90, or whether you have 270 degrees, so if that's u and that's v, okay, if two vectors are perpendicular, so another way to say that is orthogonal. So if they're perpendicular, that means their dot product, u dot v, is 0. And this works in reverse too. If u dot v is 0, therefore you know that the two vectors are perpendicular. So this is the first property. Okay. The second property is known as the commutative property. The first property doesn't exactly have its own name. Okay. All right, number 2, the commutative property. All right, so the commutative property says that if I take two vectors and I dot them, so if I have u dot v, that's the same thing as v dot u. Now, if you're wondering why that's the case, well, it's not just because it's not u times v. Remember, u dot v is in fact the magnitude of u times the magnitude of v times cosine of theta. And v dot u is the magnitude of v times the magnitude of u times cosine of theta. Well, it doesn't matter which one you put first. The angle between them is the same, so the thetas are the same. And if that cosine of that angle is getting multiplied to u and v, the magnitudes, it doesn't matter which order you multiply those because multiplication is commutative. Okay, so that's the commutative property. Now let's move on to the third property. There are going to be 4 in total. So actually, let's do this. Okay. So the third property, this one also doesn't have a name like the first one, but the property states that for any vector u, if you dot that vector with itself, you simply get the magnitude of that vector squared. Okay, so let's see how that works. If you have vector u, okay, so let's say vector u has a certain length, it's heading in a certain direction, and you want to compare it to u. Now I'm drawing them underneath each other, but in reality they would have to be superimposed. they would need to be on top of each other since they're supposed to be lined up tail to tail. But just so that you can see, I'm going to draw it like this. Okay, so what I know is that the angle between these two vectors is 0 degrees. So using the definition of the dot product, u dot u is equal to the magnitude of u times the magnitude of u times cosine of theta. Now, cosine of 0 degrees is 1, right? So that's 1, and so all you're left with is magnitude of u times magnitude of u times 1. So then I'm left with magnitude of u squared. So that's where that comes from. Excuse me. The last property is called the distributive property. Okay, so the distributive property essentially says this. Okay, so let's say you have 3 vectors. So for vectors u, v, and w, we can state the following. We can state that u dotted with the sum of vectors v plus w, well, we can take that vector and we can dot it with each individual piece inside. This is the same thing as u dot v plus u dot w. So essentially what it looks like is like you're taking this and you're distributing it into each piece inside, but you got to keep the plus sign there as well. Okay, so that's true, and if we have v plus w dotted with u, well, you know that based on the commutative property, u dot v is equal to v dot u. So this is essentially u dot something, some vector, and this is that some vector dotted with u. So you should get the same result, and sure enough, you do. Okay, so if I do this, I'm going to get v dot u plus w dot u. Okay, so same idea. And these two are the same, right? So u dot w is w dot u, and of course the same is true for u and v also. Okay, so having those properties in mind, let's go ahead and try some examples. Okay, so this is example 3. So example 3, part A, k times u dotted with u plus v. We have to figure out and simplify this as much as possible. Okay, so just simplify. So what I see here, I mean, a scalar multiple of a vector, that's a vector. And the sum of 2 vectors, that's a vector. So you're taking one vector and dotting it with another vector. So your answer has to be, well, a scalar. So whatever format our final answer has, it should look like a scalar, or at least be interpreted as a scalar. Okay, so what I'm going to use right now is the distributive property. Okay, so I'm going to go ahead and take this first vector and distribute it amongst the sum inside. So that's going to become ku dotted with u plus ku dotted with v. Okay, so now next I'm going to factor out the k. Well, it's not really factoring, but I'm going to remove it from the bracket. So it's going to be k and then keep the u's in the bracket. So that's k times u dot u plus k times u dot v. Now, based on the third property that we saw, if you have u dot u, that's equivalent to magnitude of u squared. And this piece we can't simplify, so we just call that k times, u dot v. Let me just wipe that out for a second. So that's a dot. Okay. Now, if you want, you could factor out the k. I guess that would make it look a little bit simpler, but as far as we go here, that's as simple as we're going to go. Okay, let's try another example. Part B, we have vector r plus s dotted with r minus s. Okay, so just like before, we're going to use the distributive property, except instead of having one vector multiplied by the sum of 2, we have a sum of 2 dotted with a sum of 2. So that means you have to FOIL, right? Kind of like when you would expand x plus 3 times x plus 2, let's say. So you have to dot the outside, so sorry, the first terms first, and then the outside, and then dot the inside, and then the last terms. So this is going to be r dot r, and then here you notice there's a minus here and a plus here, so that will be minus r dot s, now inside, plus, because they're both plus, s dot r, and then minus s dot s. Okay. Now, based on our third rule, I know that r dot r is magnitude of r squared, and I know that s dot s is magnitude of s squared. So I fill those in. And then based on my commutative property, I know that r dot s is equal to, well, it's the same as s dot r. So this is minus s dot r, and then I have plus s dot r, so those cancel. So they're gone. So I'm left with magnitude of r squared minus magnitude of s squared. And that's my final, most simplified expression. Okay, so those were some examples without numbers. Let's do some examples with numbers. Okay, example 4. Calculate u dot v. Okay, so part A. Vector u is given as 5, comma, minus 3, and vector v is given as 4, comma, 7. So really what you got to do is just understand that you've got x and y terms here. Now so far when we've been calculating dot product, we've been using the original formula, the magnitude of u times the magnitude of v times cosine of the angle between them. But that's not the only formula. So if we go back to our original, oh actually sorry, this is not the original, give me one sec. There we go. If we go back to our original page, okay, so we have this formula that we've been using quite a lot, but there was another formula. If our vectors are given in terms of Cartesian coordinates, so a comma b or x comma y, this is the formula. You take the sum of the products of the x components and the y components. So that's what we're going to use here. So here, I got to identify my x and y components. So here I've got 5, that's ux, negative 3, that's uy, 4, that's vx, and 7, that's vy. All right, so u dot v is going to be ux times vx plus uy times vy. That's it. So I just have to multiply those numbers and keep everything straight. So ux is 5, vx is 4, uy is negative 3, and vy is 7. So 5 times 4 is 20. 7 times negative 3 is minus 21. Okay, so 20 minus 21, that's negative 1. Okay, so that's A. B, u is equal to negative 2, 9, and v is equal to negative 1, 0. This is just like the previous problem. So we're going to identify our ux, uy, vx, vy values. So here we go. There's ux, there's uy, vx, vy. So it's same strategy. U dot v is equal to ux, vx plus uy, vy. So the sum of two products, or the sum of products. So ux is negative 2, vx is negative 1, uy is 9, vy is 0. Okay, so this side 0 times anything is 0, so -2 times -1, that's +2. Okay. The last example is a proof. Prove that A dot A is equal to magnitude of A squared algebraically for any vector A. So the only other times you've been asked to prove something is usually during trigonometric identities. Prove the left side equals right side. And so that's exactly what we're going to do here. We've got a left side, we've got a right side, and we're going to show that they are in fact the same thing. Okay, so left side I've got A dot A, and on the right side I've got magnitude of A squared. So I'm going to start off with the left side here. A dot A. Well, I know that my vector, so A, has 2 components to it. I know it has an x component and a y component. So we'll call those components AX and AY. So then AX comma AY dotted with AX comma AY. Okay, so you know how to do the dot product like this. It's x components multiplied plus y components multiplied. So I have AX times AX plus AY times AY. So that's just AX squared plus AY squared. So we have to get the right side to equal the same thing. Okay, so this entire time what we've been assuming, just before I move on to the next piece, is that vector A is AX comma AY. Now that's a pretty simple, clear conclusion. You don't have to really justify that. If you have a vector, use the same letter and just put subscripts x and y. All right, so the magnitude of A squared is the magnitude squared of vector A, and vector A is AX comma AY. Now, you know how to take the magnitude of a vector. If you have 2 sides of a right angle triangle, you find their magnitude by figuring out the length of the hypotenuse. And well, after all, the length of the hypotenuse, so that's this, right? What's the magnitude of the vectors? That's this. The square root of AX squared plus AY squared. But remember, this whole thing is being raised to the power 2. So if you square a square root, you're going to be left with AX squared plus AY squared. And sure enough, you've got the same thing on both sides. So since left side equals right side, therefore A dot A is equal to the magnitude of A squared. Okay, so that marks the end of this video. Okay, so that is the end of 7.2 dot product. Stay tuned next time for video 7.3.